with great pleasure that I am here to introduce our next keynote speaker. Dr. David Brumley is CEO for Forallsecure. He's also a tenured professor at Carnegie Mellon and has a PhD from Carnegie Mellon and an MS from Stanford University. Dr. Brumley is the author of over 50 publications in computer science and received numerous awards, including the US PCASE Award from President Obama. It's the highest award in the US for early career scientists and engineers. He also impressively won the DARPA Cyber Grand Challenge in 2012 with their Project Mayhem, which is their autonomous cybersecurity system. With that, I'd like to turn things over to Dr. Brumley, our next keynote speaker. Thank you.
Thank you, everybody. You know, sometimes I feel like offense just moves too fast and that defense is just too slow. I remember the first time I got this feeling where I just couldn't win. I had just gotten out of school and I was working as the computer security officer at Stanford University. Today, the CISO title is a big role. Right back then, it was essentially doing incident response. I remember this one particular incident where a computer was hacked and it belonged to a Nobel Prize physicist. I noticed it because the hacker got on irc.stanford.edu and I had a little script that would like do a who is of the computer, and it was kind of odd for a Nobel Prize winning physicist to be on IRC, believe it or not. So I called him up kind of nervously and said, you know, sir, your machine has been hacked. I've taken it offline, and to get back online, you're gonna have to reinstall from scratch. You're gonna have to update to the latest OS and install the latest patches. Well, the professor was really nice and polite, but he pushed back. He said, look, I'm doing groundbreaking research, and I'm not sure whether or not this custom software that we're running is gonna run on the latest version of Red Hat, which was a good point. The second question he had is, you know, suppose I do go through all this work, is this gonna be a regular occurrence, or am I gonna be able to not get hacked again? And so I spent some time with him. I helped him reinstall, and it turned out his custom groundbreaking research software did work on the latest version of Red Hat. It wasn't actually a problem. And I actually helped him lock down his system so that, you know, every service was turned off except for SSH. He had good passwords. All the patches were applied. But then just 2 weeks later, that's when I got that sinking feeling that I just couldn't win because his computer was hacked again. So I had to call him up meekishly and say, you know, hey, despite everything we've done, I've had to take you offline again. And so I went over to his computer and I tried to figure out what had happened. And what had happened is the hacker had found a 0-day in SSH and started compromising machines. In fact, this was a different hacker, right? So the hacker had broken in, and then worse than that, he started to pivot across the Stanford network. And so he scanned the Stanford network. And so I, you know, stopped what I was doing. I helped the professor, you know, turn off his machine and figure out what to do in the interim. Went back to my desk, looked at network logs, and looked at these dozens of machines, and it just felt hopeless. And so I started to reach out to the various people who had been compromised. One of them actually turned out to be google.stanford.edu. So I called up Larry Page and had the same conversation. I actually turned off Google from the internet one day. Now, I tell this story really because it was a changing moment in my life. No one likes to be in the seat where they always feel like they're losing. And so at that point, I decided to go back to school, and that's when I got the master's. I got a PhD and spent the last really 23 years doing research on this question of how do we beat attackers? And there's a couple things that stand out to me that I really learned during that time. The first is really what that professor told me, which is, look, I'm not sure whether the patches will break something. Conferences like this are amazing, and what people do at Pwn to Own is just like out of this world. But really just going out and finding the exploitable bug, while super cool, you gotta be careful not to pat yourself on the back, because until that patch is deployed, things aren't more secure. And too often in security, we forget that. We look at the problem and say, we pointed it out, we did our job, but that's not really the solution. And the second is, we have to figure out how people are finding 0 days and actually figure out how to beat them. Now, I think computer security is actually quickly reaching a crisis. Everyone's gonna tell you that, and I can't forward my slides, there we go. Everyone will tell you that, you know, hey, there's too many attackers, too few defenders. But I thought one thing I could maybe give you is a little bit of a visual. Now first, I don't think the problem is too many hackers or attackers, too few defenders. I actually think the problem revolves around the speed and pace of development of software. This is a picture of Texas Longhorn Stadium. It seats about 100,000 people. Now, on the field, there's about 200 people. GitHub now reports that there's 500 developers for every computer security expert. That means the computer security experts, imagine those are the people on the field, they're trying to secure all the software made by the developers, the audience of this. Another way to think of it is here at CanSecWest, my understanding is there's about 200 people registered. And so everyone here at CanSecWest, your job would be to secure the software developed by that crowd. It's just crazy, right? Like 501 is hard to imagine, but that's what we're working with. And so I've been on this mission to automatically check and protect the world's software. And it really starts with this idea of, can we find exploitable bugs first? And then can we fix them? And then can we test those fixes to make sure they don't break anything? And I have here that we want to test them first for functionality, even above security. When you put out a fix, if it breaks functionality, no one is going to install it. Performance is another key factor. If you have lower performance, again, people will delay. And finally, is it more secure? And then you have to deploy your software. Now, at the same time, we're going through this loop as defenders. Attackers are going through a similar loop. They're trying to find exploitable bugs. And then once they find them, they're going to go through some work to weaponize them. And that weaponization may take a lot of time or a little bit of time. We don't know. But once they weaponize, they can go and attack all our different systems. So I've actually just want to point out, I've broken out here weaponization because it is a really cool step. This is where a lot of the human creativity shines, where you have a control flow hijack exploit, but they have ASLR and def enabled in the sandbox, and then you have to put 3 together to finally weaponize it. That's what the attackers do, but still that bug exists, and we need to get rid of it. So my research for the past really almost quarter of a century now is, how do we automate this? How do we build robots that can do the boring stuff? I got really inspired by Deep Blue, because Deep Blue can look through the different states of a chess game and really beat the best humans out there. And it took a while to get there, right? You can see this progression of chess. I believe that we can do the same thing in computer security. Humans will always be needed for the creative aspects, imagining the new scenario. But we can build computers that can automate and work just so much faster than humans once that's done. So the agenda of the day is pretty simple. I just want to tell you what the art of the possible is and what we're found in research. And I'll give you a couple anecdotes from my own personal life. I also then want to switch to what is the go-to-market to change the art of the practice in the status quo. The reason I want to touch on this is often we present papers. In fact, this has been my life of presenting papers. You get a best paper award and you're like patting yourself on the back, and yet nothing changes in the market. And so, to quote the Beatles, what's the plan? We need a plan to take that research, to take those best practices and get them to the common developer. And I wouldn't just say it's a research versus for industry problem. You also see this between companies like Google and your small and medium-sized businesses, where small and medium-sized businesses are like, that's great for Google, they print cash, they can hire any developer they want. We can't. How are we going to go about this? And then finally, how you can help. So it started actually in 2014, not 2012, where DARPA asked this question: is autonomous attack and defense possible? This was asked by a DARPA PM named Mike. Mike was part of actually a winning DEF CON team. He had a black badge from DEF CON CTF. And he said, look, what humans do in DEF CON CTF is amazing, and it's really representative of this micro universe of attackers are breaking into systems, and defenders have to prevent that. And so let's see if we can teach computers to do that. I'm going to put $60 million of US taxpayer money into this, and I'm going to offer a $2 million cash prize if you can show it's possible. And they called it the DARPA Cyber Grand Challenge. This was not a name chosen idly. DARPA does not do grand challenges often. They did the first grand challenge was self-driving cars. And they call them grand challenges because the possible answers are both yes and no. In fact, the first self-driving car challenge, the answer was no. None of the cars went more than a few feet. So they put out this challenge and said, hey, there's all this research, all these great claims. Is it actually possible? And so I'll give you a little bit of the setting here. The setting was, first, when we talk about finding exploitable bugs, there's some amount of creativity in defining what a bug is, right? Like before people studied timing attacks, people didn't know to look for timing vulnerabilities. But here we're going to say they're standard execution monitor enforceable properties, if you want to know the definition, think of this as just something that a runtime monitor can detect. At some point, you've gone from a bad state to a good state. You've overwritten memory, you violated a password policy, something like that. It's going to be machine only, no human. So the systems are going to sit up there, and not only do they have to deal with attack and defense, they have to deal with things like disk failures. And then finally, and I'll touch this because this is really a big impact when you look at your go-to-market. The attacker and defender both host and can run the app in their own hardware. And so if we go back to this picture, all these computers were running the same binary software, no source code, and the goal was to go and find exploitable bugs, attack your adversary, break into them, you got a point, and if they broke into you, you lost a point. I want to come back to this, so put it in the back of your mind. It's going to be really important when you talk about go-to-market, because this is actually one of the first assumptions that can get violated. So the status quo when we looked at this problem was really to use static analysis. Now, when I first went back to Stanford, I studied with a person named Monica Lamb. She's kind of famous because if you've seen the Hackers movies, they talk about the Dragon book. It's a real book in compilers, and she's one of the authors of it. And then I studied with a guy named Dawson Ingler as well. Dawson Ingler, in his research on metal, became Coverity. And so I'm well versed in this idea of the status quo as static analysis, and it's got this beautiful kind of alluring vibe to it, where, we want to beat attackers. So what I'm going to do is I'm going to run this tool. And this tool is going to find every possible exploitable bug. I'm going to have this big checklist, and if I can just get through them, well, then I'm going to be safe. And then, of course, attackers, if that works for defenders, should also be doing this. What we should be seeing is Project Zero running static analysis tools to go find those exploitable bugs, because you're going to find all of them. And as long as your tool is good enough, it's worth going through. Certainly at the nation state level, when you're looking at hard targets, you would go through long, long lists with the idea of just finding that one possibility. Now, at Pwn to Own 2021, there was a drone attack where a drone was shown to take over a Tesla with a zero-click exploit. The problem was in DHCP, in a DNS proxy. But if you think about it, what static analysis tools are doing is they're essentially just highlighting a line of code for a human to then go and triage. This is the actual line of code from CanSecWest 2021, where there's a possible out-of-bounds mem copy. There is an out-of-bounds mem copy, and this is what the drone ended up using to unlock the car. So this is the status quo. This is the idea. We're just going to create this list. But it turns out it doesn't work for a couple of reasons. First, by definition, these tools have false positives. And we can get into the theory of why, but by definition, they're going to have false positives, which means you need a manual person to check the results. Essentially, you have a security tool who can lie to you. It's an over-approximation potentially, but it's lying to you, and so you have to have a human. And so that technique wouldn't work. But more importantly, what we found is static analysis had insufficient fidelity. There's a big difference between an exploit and a vulnerability. That mem copy may be a vulnerability, but whether or not you can exploit it depends enormously on low-level details. You could have a buffer overflow in C that can't be exploited and is not actually a vulnerability when you compile the code because of things like page-to-line compilers when the compiler page lines. And so this dream of static analysis didn't really match reality from the defender standpoint. The second point actually from it is every time you go and change software, you're going to have that same problem Robert Laughlin, the Nobel Prize physicist, asked me, which is how do I test that change to make sure nothing broke? And you can't do that really with static analysis. All you know is your checker, that black magic, stopped reporting an error. So it's untestable true positives as well as there's no way to help test the patch. And so when you want to automate this cycle, it doesn't really help for someone to come up and give you a long line of maybes. It's not so actionable. And my experience has been when you go and look at attackers, they don't typically use static analysis, not in any sort of real capacity. And I could be wrong. I'm basing this on my experience at CMU, where I've had the really privilege to work with some of the best hackers I've ever known, people like Fluorescence, who have won Pwn to Own, and George Haas. And I've never once seen them use the static analysis. And so when you go and look at this, we all quickly arrived on this idea that we want to use dynamic analysis. And I want to emphasize, this is actually a pretty radical difference between how we went about automating and what the status quo thinks you should do. And really, I think it gets at this idea of the difference between a vulnerability and exploit. What you're trying to do is defend against exploitable bugs. An exploit is that drone opening the doors. That line of code is devoid of those details. You want to create the thing on the right, the thing on the left, in. So the technical intuition of why this didn't work is Really, when you think about it, there's okay code and there's buggy code. You can think of this at the per function level. You can think of entire functions. It doesn't, entire programs. It doesn't matter. So here we have 10 different, let's call them functions, right? And you're going to run your static analysis. That's one of the approaches. Really, the big lie in academia is when you go read an academic static analysis paper, they always talk about soundness. And what soundness means, actually, if you read the definition, is if I say it's bug-free, it really is bug-free. There's nothing in that definition that talks about finding a vulnerability. In fact, what happens is they just say, well, I couldn't prove it was bug-free. You got to go look at that. Maybe it's vulnerable, because we can't verify it's bug-free. So there's a little bit of a lie there when you look at static analysis and you look at academics and how they write papers. Now, this guy Dawson Ingler I mentioned, absolutely genius. What he does is one day at Stanford, before he had 10 years, he said, look, I don't care about soundness. I don't care about pushing theorems. I don't need to prove how smart I am to anyone. I just want to find bugs. I'm going to make a tool that's neither sound nor complete. I'm going to find something that just goes and looks for bugs. And what he did is they would parse a program, create an AST or a control flow graph, and then look for little patterns. And essentially, if you go look at all commercial static analysis tools, this is what they do today. They're looking for patterns. And maybe on the control flow graph, they may say they do data flow analysis, but again, it's not really academic. The problem is they have both false positives and false negatives. In fact, if you go look at the statistics, it's very hard to find big ones because these are often commercial tools. But typically, you're going to find the actual detection rate, the true positive rate, is only 50% of the known vulnerabilities. Plus, again, it's non-actionable. And then what you'll find is as soon as you get to a detection rate of 50%, you also end up with a false positive rate of 50%. So you have this kind of tune thing where you can lower false positives, but you lower your detection rate as well. And so there's a little bit of a lie here. And I just wanted to point out, when you say static analysis, industry static analysis and academic static analysis use exactly the same word, but mean completely different things. Now, there's been this growing area of research in dynamic analysis. When I started at CMU as a professor and where I started doing research, I was really motivated by this. Because what I could do is I could actually run the executable code. I was working at the fidelity of finding the exploitable bug. And I thought, just even more importantly, there's a lot of closed source programs out there. If I can develop tools that work on executable code, well, then I can check the security of that code myself. I think this idea that developers, as soon as you find a vulnerability, you need to tell the developers, I'm pretty sure that's right. But I also think many developers don't care or don't have capacity to deal with that. We need to enable it so everyone can check the code that they're going to execute. And so dynamic analysis had this. Now, the cool thing about it is the longer you run it, the more you'll find. It's a different mindset. It's not a scan and sweep. It's really much more like an attacker, where if you give Natalie 2 hours, she won't do as good as if you give her 2 weeks. She's going to find more and more and deeper results. So when we went down this area, there was really 2 approaches that we could take. There's coverage-guided fuzzing and there's symbolic execution. I think we're all pretty familiar with coverage-guided fuzzing, and so I'll just kind of briefly define it. Really, I think one of the things that we need to do as a community is stop calling fuzzing random testing. As soon as you do that, everyone thinks it's dumb. That was certainly fuzzing back when Mark Miller did it, back in 1980. But, I mean, come on. Big hair was popular then, too. So really what it is a negative testing technique that generates inputs with the goal of eliciting new code coverage. The idea is that all an exploit is an input that triggers previously under-tested code, where it takes a known input, mutates it, runs the program with the mutated, and keeps the mutation if coverage is improved. So, for example, you may come up with a mutation x equals 120, run the program, and see, it took this program path, that's new code, I'm going to keep it. Now, if you run that exact same program on input 122, it takes the same path, you're going to throw away that mutation because it doesn't execute new code. And you're going to do this as quickly as possible. There are amazing tools like AFL, LibFuzzer that do this. One of the big things that we were looking at is, can we do this with binary code? And I think we can, and I think others can as well now too. But there's 2 problems with this. First, it's unlikely to hit very delicate conditions. So here I have this, if y equals a very particular integer, jump stack. Now, jump stack, of course, being like a return buffer overflow. Now, it's very unlikely to pick this particular value of y. Now, there's various heuristics that people can pick. For example, you can say, well, I'm going to look for comparisons, and I'm going to pick things that meet that comparison. Well, that doesn't work here because y is actually calculated from x. It's x squared, right? So just saying I'm going to input a y that's dead B4, B04 is not going to work. The second is, and this is really important, that coverage doesn't necessarily mean that you found all bugs. Here we have, at the very bottom, divide by 0, right? If I is 0, you get undefined behavior. You get a processor exception if that's an integer, or I'm not actually sure what you get if you're floating point. You get a sigfp, certainly if it's an integer. The point of this is that you don't just want coverage. Coverage is like a heuristic, but it may not talk about different behaviors in the program. So the idea behind symbolic execution was, look, what we're going to do is we're going to pick a program path, and we're going to be able to mathematically model that program path in first-order logic. And so instead of executing on a concrete input, we're going to execute on a symbolic input, and it's going to create a formula. So for this path, x is greater than 100, and then x is, less than 100, and y equals x squared, and so on, to create a formula that's true for the path that we've selected. Now, if we want to execute a different path, we can just flip a branch condition. So we can just take this formula and say, oh, well, the first time I went down this program, I executed that last statement, z equals y divided by I, because this branch above it failed. Let's flip the branch condition and create a formula that's satisfiable when we take the branches that we want. And then we can give this to an SMT solver that will give us an input that takes that selected branch. And so really what we've done is we've taken a program, and we said, look, programs modify state. The difference between that and first order logic is pretty small. We just have to make it so it doesn't modify state. Give it to an SMT solver, and we can, by definition, generate an input that takes us down the selected path. And we can just iterate this over and over again to go and get more and more coverage. So the second problem that we ran into is not just getting coverage, but how do we go from just triggering a particular piece of code to actually generating an exploit? And we started working on this problem, and we called it automated exploit generation. The funny thing about it, and I think this was kind of our big idea, or the big idea, not just by us, but by others, is it's really verification with a twist. Typically in program verification, you're going to take in a program and you're going to try to verify a correctness property, and it's going to output whether it's correct or incorrect. Now, the reason that we can't verify programs automatically is because there's loops. We have our good friend, the original crypto hacker, Alan Turing, who proved undecidability for programs, and then we have Rice's theorem, which follows. We know that without human effort, you can't do this fully automatically. But the twist is, if we look at programs path by path, now you have a finite state machine. Now it is decidable. And instead of looking for correctness, well, correctness is just whatever you write down in logic. I can write down in logic and overwrite a return address and put my shell code here. And if I tack that onto my condition in symbolic execution, I can then not just generate an input that takes me down the particular code that I want to execute, but also generate an exploit. So this is what we were working on, POC exploit generation completely automatically, where we generate the formula. The formula would take us down the program path, and then we found something like, oh, EIP is user controllable. Let's add in conditions to actually put in our shell code and launch. So we were pretty excited about this. We're automatically generating exploits. We published it in academia. It got great reviews. It got accepted. But funny thing, just kind of a fun anecdote, is in industry, people hated this paper. I got tons of hate mail saying these aren't real exploits. You can actually go find those today. The point is that we were not trying to say, hey, humans who are doing ROB aren't doing something that we can't do. What we were trying to do is saying we need to push the state of the art about what we can do, because there's just too few humans to do this sort of thing. And so we continued working on it. What's kind of funny is these are kind of standardized techniques today. It was funny, last year I read a GitHub blog that says we need more research in automated exploit generation. And this is what we were doing. The other funny thing about this is that actually the corollary is that any advances in verification technology will also help adversaries. If you think about it, typically when you're working about program correctness, you're trying to verify it's correct. You can just add in correctness means I can exploit it, because for an attacker, that's what it means. And if you verify that property, well, it's exploitable. Kind of a cool thing. So as we were doing this, one of the things that we found was that building symbolic execution is a really interesting area. That's because it requires high precision. I want to give the analogy. It's a little bit like building a space shuttle or a rocket. When you have the space shuttle, if you have one misplaced ceramic tile, game's over on entry. Or when you're building a rocket, if you're just a few degrees off, it'll go to the wrong place or to blow up on the launch pad. Symbolic execution is like this. It doesn't tolerate errors well. And so there was a lot of research that we had to do. For example, how do we maximize returns on symbolic execution? We're going to be asking a SAT solver to solve this formula. We know that's NP hard, NP complete. How do we do that quickly? What do we do about exponential size formula generation? How do we work with SMT? So by definition, SAT solvers are just heuristic engines. How do we work with those efficiently? Smart formula generation and so on. And so if you read the research in this, and this is still ongoing, this is what people are doing. So I'll give you a couple of kind of interesting quips. So the first thing is, how long do queries take on average? So I'm going to create a query, give it to an SMT solver. It actually takes 3.67 milliseconds on average with a 0.034 variance. What this means is that when you give it a query for a path formula, it's quick. Should I optimize hard or easy formula? We ask this question because when you go and you look at researchers, they'll often say, here is a place symbolic execution did not work because things got too hard. What if it got too hard? And it turns out in practice, that's not the barrier. 99.99% of queries take 1 second or less and account for 78% of total time. That means you get more bang for the buck making easy queries even faster than taking a hard query and making it a little bit faster. You're going to get better scientific throughput. Another question people would ask is, do queries get harder the deeper that you go? They'd say you're building this formula, and of course the math gets more complicated the deeper you go, and that's a really good question. Turns out it probably isn't the case. This is a 4D graph where we show the depth of execution on the x-axis, the time to solve on the y-axis. We have a color coding for the number of nodes in the size of the formula, and then we return whether it's satisfiable or unsatisfiable, right? Because you could have different behaviors, whether or not you can solve it, satisfiable, or can't solve it, it's unsatisfiable. And what you really see here is there's no upward trend where as you get more and more deep that you cannot solve the formula. Let me actually put it on a log scale to make it a little bit easier. What you see actually is size is not correlated with hardness. When formulas are small, they're almost always satisfiable. You know, if someone says x is greater than 2, it's really easy to find an x that's greater than 2. And when formulas get really big as you get deep, often you'll immediately find two different things that contradict each other. You'll find one statement that says x is greater than 2 and another one that says x is less than 2. Immediately, you can throw away the rest of the formula and say it's unsat. And really, there's this area of search in the middle where things get difficult. It's called the phase transition, actually, in SAT. And so there's kind of this medium that actually is hard, the hard part. And then, of course, as I said, exponential program. Typically, what people do is they generate a path formula, and there's an exponential number of paths for a fixed number of loops. And we ended up publishing a paper called Veritesting to avoid exponential formula explosion. It turns out this technique was so valuable that we used it in CGC, but also the number 3 team used Veritesting in their approach for solving this DARPA challenge. So what do we do? So at the end of the day, I did all this academic research in symbolic execution. I had kind of fallen into the same trap that I accused static analysis of. I could push formulas, I could push logic. It was easy to write papers about. It turns out in practice, actually, you want to combine it with fuzzing. And the intuition for that is fuzzing runs really fast. You have this, essentially, this fast guessing behavior. And if you can just guess really, really fast, often you can come up with the right answer really, really quick. But there's these cases where fuzzing will get stuck, like the one I showed you. And that's where you want symbolic execution to actually break through. And so what the best research shows today is you want to run a portfolio algorithm. Not just we're saying this. There was also a great paper called Driller from the UCSB guys that showed really when you run these things together, you're going to get better results. I mention this because sometimes you'll read people say, I tried fuzzing, I didn't try symbolic, symbolic's too hard. What this shows is really the portfolio is the best approach. So when we get back to this idea of can we automatically do what attackers do, the art of the possible is yes, we can. Essentially, what everyone has concluded is running a portfolio of symbolic execution fuzzing will give you the best performance for finding exploitable bugs. It turned out this patching problem was not the hard one. Going in and saying, okay, I have an input that triggers this buffer overflow, this divide by 0, this logic bug, coming up with a patch that just prevents you from getting exploited is not hard. The hard part is testing it. And this is where actually symbolic execution shines through, and I don't think security researchers actually appreciate this. What we would do is every time we found a bug, we propose a fix, and actually a set of fixes. And then we would take that test suite created by the fuzzer symbolic execution and run it and measure functionality, performance, and security. And then we would only field the patches that met our overall business requirements. So we could actually propose 10 patches, see which one worked the best, and then field the most appropriate one. This is something that if you go look at static analysis, they can never do. Static analysis can never auto-patch. They could propose a patch, but because they can't test it, they're always going to require a human. Now, on the find the bug side, this was a really fun place. We could weaponize automatically, and we could do things like control flow hijack. We could do memory disclosure. And of course, there's limits to this, but it is an area that people are working on. So the art of the possible is yes. I think this gives us hope. When you go back to this idea of there's, in a football field, there's 200 people on the field and 100,000 in the stands, we can do what we can do best. We can leverage superior technology, better engineering to get ahead. So it is possible. So I want to take a few moments to talk about the status quo. So after we won the Cyber Grand Challenge, we were super excited, probably a little bit full of ourselves. In fact, Mayhem won it. We won $2 million. We used that to kind of bootstrap our company. Mayhem then went on to play in DEF CON CTF, and though it didn't win, it still did reasonably well for a machine. I thought that was pretty cool that it could even be competitive with someone like Fluorescence at Pondo. That we could, Mayhem found exploitable bugs and created exploits for ones that PPP thought were unexploitable. The top hacking team that year. But then we went out and we said, okay, we want to bring this to market. What are going to be the challenges? And we thought it'd be easy. We thought, you show people the art of the possible and they'll follow. I'm sure you've all heard the story of VHS and Betamax. Betamax was a superior technology for VHS, but VHS won. The best idea is not always the one that wins out. It's a beautiful thing in engineering we think of, but it actually is not the truth. So to recap the state of the art possible, $60 million was invested showing this was possible. Google, since then, has launched OSS Fuzz with incredible success. Microsoft's software development lifecycle requires fuzzing, which is this core ingredient to do automated testing, automated verification, even automatic exploit generation. And even at CMU, we had started to run this at a large scale to really look at this law of large numbers, where we looked at 32,000 programs, found 2 million crashes, 11,687 previously unknown bugs, and we were able to generate automatically 152 control flow hijack exploit POCs, right? And so this is starting to show, hey, the real advantage is you can start applying these things at mass. Maybe if you give me 100 programs, you give me this one, I fail, but the other 99, I succeed on. That way the human is reduced to only having to work on one. So why isn't everyone doing this? Well, I found this quote, and I hate to go out and just kind of quote random people, but I think it's a good one, where Steve Jobs said, to me, ideas are worth nothing unless executed. They're also just a multiplier. When you go and you try to raise VC money, for example, you start talking about your patents, and VCs don't care about your patents. Those are just ideas. What really matters is the team. Can you execute? And so I want to talk about how we're executing today and some of the things we learned. So first, I invite you just to go to forallsecure.com. You can go and actually try our tools today. I'll show you what it looks like, in fact. I've got to get out of this new window. So one of the things we've worked really hard on doing is making sure that our interface is pretty quick, pretty easy to use. So I want to go over a little example. One of the examples that we've often used is a web server called Lighty. And we'll look at a well-known vulnerability. If you go to our website, you can actually find 0 days in the last few years. But this one's been well-known out there. The reason I use this example is because it's really illustrative of the problem out there. So Lighty is not just a web server. It does SODL open, so it loads in dynamic libraries. It has a configuration file. In some configurations, it may be vulnerable, and some it may not. It's really important to get all those things right. So it's running across the world even today. And in fact, sadly, it's used on Siemens controllers, on GRPS routers that are basically VPNs for energy systems out there today. So one of the things that we've really tried to work hard on is how do we make it easy? And what we've settled on is this idea of you can take in a Docker image. And so if we just search, we integrate also with Docker Hub. You can pick out a Docker image and hit go. And we're trying to get away from all that configuration typically you'd have to do in fuzzing. So Mayhem handles network inputs without any harnessing. It handles binaries without any harnessing. You can say you can run forever or specify a runtime. Well, actually even automatically pick out the command that we should be trying to break into from the Docker image run command. And we have some things like we can do advanced analysis or just more basic analysis. And then you just click run. So there's a couple things that we do here. The very first one is we first are a distributed system, so we go get workers to do it. In the top right corner, you'll see exploitability factors. We try to measure, is ASLR enabled, our stack piece, our dev. Natalie just said these actually are real things that make exploiting real harder. And it's a lightweight thing that you can just automatically check, so why not check it? It makes weaponization harder. But then Mayhem just goes and it starts creating a test suite. And so it's running here, what, 1,000 executions per second. We go and we do what's called min setting. So we take all those executions and reduce it to the minimal set of inputs necessary to reproduce all test cases. By the way, if you go read the AFL source code, their idea of min setting is wrong, as well as the fuzzer. There's actually an algorithm for doing this. And then, of course, when we find a bug, we'll go through it and we'll triage it. And so it's already found the bug. Now, the key thing, the thing that I love about this approach is when I was doing static analysis research, I'd have to go manually and triage everything. Here you get a test case. And so here's one test case that triggers what? 10 different vulnerabilities or 10 different issues in the code by unique stack trace. Even better, when you're trying to convince someone, if you go out and say, hey, I'm a product and I have 0 false positives, people just kind of shut off. They think that it's marketing. But really what I'm saying is I actually don't find vulnerabilities. I find inputs that trigger bugs, and then later on I figure out that they're vulnerabilities. It's different. Where if you simply take the output of the tool, you can just replay it, and here it's crashing the web server. Now, this isn't a weaponized exploit. We actually removed the weaponization from our commercial product because why do it? But here's something that's very convincing to people. Hey, I just gave you an input that can crash that server. It also, people will tell me if you go and you take a package and you harness this one function, you can get higher execs per second and find more bugs. That's true. But then you have to manually backtrace. And so there is a little bit of a pro and a con here where the more you do that, you're adding a human to the loop. And so we're trying to work on, can we make it fully automatic? Even if, for example, this has other, it's not perfect. That's Mayhem. Anyone who wants can go to actually mayhem.forallsecure.com and get a free account. All right. So I wanted to mention a couple of things that were surprising to us. So there's a beautiful paper. I recommend everyone read it from Dawson Engler, who, as I said, he revolutionized static analysis when he said, look, I'm not going to be sound, I'm just going to find bugs. He wrote this paper about, okay, we now commercialize coverity. What did we learn? And I find this really interesting because the things he talks about here are actually often the gaps you still see today between security or researchers and what you find in practice. In fact, this is a beautiful quote. However, the problems we encountered were not the obvious ones. So for example, one of the obvious ones is he ran this and his tool worked great on GCC compiled code. Remember, this is like 2000, 2005. Everyone was using GCC, Clang didn't exist. And then what he found out is, hey, I went out into industry and people didn't use GCC. They used Borderland C++, or they used this old version of GCC that didn't parse the same way we did. I challenge you, go take an old version of objdump, like one from 10 years ago, and try to compile it with a modern GCC. It just won't work. And so those are the sorts of problems you have to deal with when going into practice. And so I believe that what we need are more onboarded projects, more than advanced research. People will often go and say, what about this new paper? Why haven't you worked on that? I don't care about that stuff anymore. I think the state of fuzzing, the state of symbolic execution is good enough for me. The problem is, how do we bring more of that world software into this ecosystem so that we can automate better and better? So a couple of things. First, user can upload an app easily. Well, I showed you Lighty, you pointed at a Docker image. The reason that we did that is because Docker fully encapsulates the runtime environment. It has the shared libraries. It has the configuration. Those are DL open shared libraries, so you can't just figure them out by yourself. The reason that we did this is when we first released Mayhem, people would have to upload the binary, and it was super error prone. Where people would upload the binary, run analysis, it would fail. Oh, I forgot the configuration file. Run it again. Oh, it'd fail. I don't know why. It turns out there's a DL open. And it was just a terrible user experience. And this was a huge barrier. And so we made it easier. We thought, hey, users already done some testing and can write a test harness. What we found is security people cannot do this. In fact, even developers don't do this. This is a graph, a survey taken from JetBrains on C-specific results, where my favorite answer here was, which unit testing framework do you use regularly, if any? And 23% said, I write unit tests but don't use any framework. 46% says, I don't write unit tests for C. The largest answer here is they just don't do it. This is why everyone's worried about things may break. Now, I would say, I also think that one of the things we've learned is developers at least can write unit tests. What we found in the general security community, if you go to a random company and you said, hey, we can fuzz your software, and for some reason we don't handle it out of the box, you do have to write a harness. Don't talk to the security person about it, talk to the developer. And don't call it a harness. Say, hey, do you feel like you should write a unit test? And they'll say yes. Don't worry. All you have to do is write the unit test framework, and fuzzing will just work on it, because they're basically the same thing. Security bugs are value propositions. We've gone to company after company, and we run into problems with this more often than not. And that's because the subtle thing that vulnerabilities and exploits are two different things. What fuzzing, what symbolic execution, what mayhem does, it goes in and it finds an input that triggers a problem. We don't actually find a vulnerability right away. We have to do a triage to figure out that was a vulnerability that caused that problem. Well, static analysis goes and finds lots of problems. So what happens? You go into a sales call. The CISO has heard it all before, and he says, hey, here's some important software. If you find a new vulnerability everyone else missed, we'll buy your product. Well, what does that do? That really creates an economy where, as a product, I'm going to try to lower the bar for what I consider a vulnerability. I'm going to try to find something. Because God forbid I go into a sales call and I find nothing. I always wonder what these people would do if they went out and looked at formally verified code. They'd probably still find a problem of some sort. But what we did find is generating that test suite is a huge value proposition. I'm so surprised more security people don't do this. We recently went to a company that had to get 100% assembly coverage. It was part of one of their ISO requirements for automotive. They were factoring in 185,000 man hours just to create test cases that executed every line of code. We were able to automatically build a test suite in about 30 minutes on one of those apps that did 80% of it, just for free. Now you may say, well, fuzzing and testing are different. Testing, you assert a particular condition. These are problems that are pretty easy to handle. You run fuzzing, you see what the output is, and you just assert it at the end. Now you have a test case. Now we're not saying humans shouldn't come up with test cases as well. We're saying for things like code coverage, these are easy ways to meet them. The other thing that was interesting is we first thought, okay, well, we don't need to keep looking at open source. So we don't need to look at the OpenSSL again, because people have already fuzzed those. But what we found is this is untrue. In fact, I don't know if it's mathematically true or just an informal result, that 40% of all OSS fuzz bugs are regressions. What that means is you generated a test case, the developer changed something, and now that test case is failing. Think about it, that's what test cases should do. And so one of the problems in fuzzing, and one of the things that we tried to solve is, you fuzz something, let's keep that data set. And then next time you upload a new version of the app, we can replay it. When you try to do these sort of things ad hoc, it's really easy to say, oh, I ran it, I found a bug. Oh, can you show me how to reproduce that? Well, it's on this other computer at home. Coming up with a system to store all that was super important. So those are some of the lessons we've learned. I also want to talk about how you can make a difference here, because I'm really passionate about everyone needs to be able to check the security of the software they run. So one of the things that we did is we unleashed these two products for free, Mayhem for Code and Mayhem for API. The reason that we did this, I'll share something I've never shared before. So when we got our Series A, we went and said, we're going to be an enterprise product. We're going to go sell to enterprises. Because when you want to be a company, you have to have income to pay your developers. It's a funny thing. Everyone wants, I don't understand why they want money, but they want money. And so you have to sell something. So we were going to be an enterprise, and of course we're not cheap because developers' salaries are expensive these days. So 2 years ago, I actually got cancer. I had head and neck cancer, and I went through treatment. I had this really cool scar here where they did a neck dissection and took out parts of my tongue. And it was really painful. And I had this choice, actually, at that point. I was out for 9 months. And I said, what do I really want out of my company? And it may be a little bit fatalistic, but I said, okay, obviously everyone wants things to succeed, but what do I want if my company fails? And I decided at that point, I really want people to have used the tools and to have an impact. And so that's why we made them free, was that it wasn't like, okay, there are go-to-markets for this. It is part of our plan. I won't lie there. But it was, what if we don't succeed? And how do we change that world? The other thing that we started doing is hosting free training sessions. If you go out to universities, really smart kids don't know DevOps. Really smart kids never set up a GitHub action. They can learn in 5 hours. So we started going to universities and teaching. This is at ASU a few weeks ago. We had 450 people sign up, and we could only fit 200 in the classroom. 180 showed up. They were there for 5 hours. Now, as a little thank you, we actually paid them $100 at the end. Why did we do this? I did a little bit of math, and I figured students would rather me give them $100 in cash than spend $100 on food for them at the event. Second, so if you want to have one of these events at your university or your nonprofit, we're happy to throw one. Second thing is when you go and you look at OSS, everyone's like, hey, developers need to get smarter. They need to write secure code. I got to tell you, developers don't give a shit. This is from the Linux Foundation. What it says is when you go into development, really what you're doing is you love creating and solving problems. You love writing that new functionality. And maintaining it isn't necessarily your biggest passion. This quote from it, when asked what would be the most beneficial contribution to FOSS project, survey participants pointed out bug security fixes, free security audits, and simplified ways to add security-related tools to their CI pipelines. This is why we actually go and teach students about DevSecOps so they can do this for open source. If you think about it, actually, in this, I'll probably get shot for this. It's kind of true also with security people. Security people don't necessarily write the most reliable code. And often that malware that was installed isn't necessarily bug-free and not exploitable itself. So maybe it's just human nature, where really what we need to do is pair those people who do care about improving software quality with those who are creating the new features. It's not asking the people to do more or already working for free. It's pairing the people with the right interests. And so we started this Mayhem Heroes project, and you can find Google OSS Fuzz, great program, we're not the only ones, where we pay people to integrate these sorts of techniques in their pipeline. What we offer is $1,000 per qualified OSS project, anything that has over 100 stars that's not already integrated. We're doing this, and you can see this is very low qualification, because what we need to do to change a market is you need to get enough people doing it before it's a thing. If you go out and you say, is fuzzing a market? Fuzzing is not a market today. The only people who know this word are here in this room. What you have to do is you have to go and they have to see it in GitHub. They have to see this is a normal thing. People want to follow what others are doing so they can innovate on what they care about and just follow everything else. And so we're offering this $1,000. In fact, we have one of those kids from ASU, I think has made like $20,000 so far over the last 2 weeks just doing this. And you can go to this website if you're interested. So I'll go back to where I started. We need to automatically find and fix exploitable bugs. Human effort just doesn't scale. People have been working on this problem for a while. A while ago, 2016 was a long time ago, 7 years. The art of the possible was set. And really those techniques, not a lot is different from what we learned then. What we really need to focus on is building that market and that awareness. Instead of looking at why you can't, start asking why you can start doing this. What can you chip away in that life cycle to make it so people are using it? And we really want to do this so that humans get out of that crappy job like I had, where you're just feeling like you're never going to win. Because we can move faster than attackers. We can make defense automatic. We can win. We just have to let the computers do what they do best so that we can do what we do best. Open to questions.
All right. If you can raise your hand, I'll come around. That mic's dead, so we'll share this mic, unless this one's still working. I'm not seeing any hands. There's got to be a couple of questions. All right, there we go.
Thanks. A great talk, really interesting. So you talked about testing open source software. The thing that I actually spent months struggling with was Log4j.
Mm-hmm.
Could you comment on if Mayhem was run against that code, what would have happened?
Yeah, well first, hindsight bias is always awesome, and every tool will always find yesterday's vulnerability. So yes, it will. We ran it, we found it. There's fuzzing tools for Java. One of them is called Jazzer, very nice, supported by Google OSS Fuzz as well. And it will find this sort of thing automatically. Yep, so Log4j, it could have been the case. I can tell you something that's also interesting. This is just kind of fun for security people. There's a lot of vulnerabilities in parsers out there. So if you want to be kind of centric to this room, if you go look at like IDA Pro and Ghidra and all their parsers, there's probably still 0 days.